Yeah, in the interest of time, let's move on to our next speaker, Marco Pavone. And uh, Marco Pavone is a professor at Stanford University, and he's also the director of Autonomous System Laboratory and co-director of Center of Automotive Research. And without further ado, uh, it's all yours.
Thank you very much for the presentation and introduction, because can you see my slides?
Yes, I can see.
Great. So it's a pleasure to be here for this workshop. My research broadly focuses on the design of planning and decision-making algorithms for autonomous robots. And in this talk, I will provide an overview of my work towards safe learning-based controls for autonomous systems, which hinges upon a careful blending of techniques from optimal control and machine learning. Now, let me start by saying that the learning-based control is not the right solution for all problems. In many cases, the system that needs to be controlled can effectively be modeled by using a combination of first principle derivations and standard system identification tools, and then control with the simple feedback control schemes. Yet, future applications of robot autonomy will entail the control of the systems whose dynamics are very difficult, if not impossible, to model with traditional tools. Specifically, my lab focuses on two application domains where learning-based control can be viewed as a necessity. The first domain entails the control of autonomous robots, in particular self-driving cars, operating in highly interactive settings. For example, here, I'm showing you a very typical setting where some vehicles want to merge into a highway. And we would like to do so very efficiently with a self-driving car. Now, modeling human behaviors requires sophisticated learning-based models. And the safety-critical nature of autonomous driving makes this setting a case in point for safe learning-based control. The second domain that my lab focuses on pertains to the control of robotic systems operating in complex and possibly previously unseen environment, particularly in the context of aerospace robotics. Before joining Stanford, I was indeed an employee of NASA JPL. For example, here on the right, I'm showing experiments we conducted a couple of weeks ago on the International Space Station, where a robot grasps surfaces and manipulates objects in zero gravity by using gecko-inspired grippers. It is grippers, and these grippers are showed in the top right figure. These are grippers that, by exploiting directionally aligned microfeatures, become adhesives when loaded in shear stress. Now, this is something very difficult to model with traditional tools. And in general, the uncertainty of the environment, coupled with a very complex and often stochastic nature of the dynamics, makes this another case in point for safe learning-based control. Now, in the rest of the talk, I'm going to give you a little bit more detail on my work toward enabling safe learning-based control in these two different domains. Let me start with the topic of safe control with learned human models in the loop. Now, in my lab at Stanford, we have developed a general model to forecast human trajectories, which we call Trajectron++. This framework is based on a conditional variational autoencoder model and can ingest as conditioning variables for the predictions a vast set of heterogeneous data, from dynamical information, of course, a pedestrian moves in a way that is different from the way a vehicle moves, all the way to maps and code information, such as road boundaries or crosswalks, all the way to human silhouettes to properly, for example, predict pedestrian movement. Now, the end result is a Trajectron++, which is a generative model of human trajectory distributions that yields state-of-the-art performance on a variety of datasets. And all the code, models, and data are available at our GitHub web page. Now, how do we use this learned model for the purposes of safe control? The idea is relatively simple. We consider a set of motion primitives for the robot. The Trajectron++ is a generative model, so we can basically sample future trajectories for the humans in the scene. And for each motion primitives, by doing so, we sample the model, as I said, to produce a possible human responses. In actuality, for the case of a self-driving car, we look at about 4,000 action motion primitives, action sequences, a sample almost 100,000 human responses every 0.2 seconds, more or less. And this is enabled by leveraging a GPU implementation. We score then the best action sequence, we drive the first chunk of it, and then we plan in a receding horizon fashion. Now, in our base approach, we consider average performance. That is, for each motion primitive, we sample a bunch of human responses, and then we aggregate all those responses by using the average of a given reward function that accounts for different objectives, such as collision avoidance, desire to get to the destination as soon as possible, and so on. Now, we do have a distributional information, so a fascinating topic that I won't be discussing today is how actually we consider a risk-sensitive formulation as opposed to an average performance formulation. That is how we could swap the expected value operator to a risk measure rho. This is a fairly fascinating topic, but also a fairly complicated one. I won't go into the detail today, but if you're interested, I refer you to a sort of a position paper that I wrote with a former postdoc of mine, Ani Majudmar, now at Princeton. Now, how well does it work? And is it safe? Well, let's consider a simulation of this procedure whereby we have a human-driven car and a robotic vehicle. So this is a human-in-the-loop simulator whereby a human, a student, drives the car and the blue vehicle, and the robotic vehicle is driven by our algorithms. The simulator is based on Bayes VTD. The task is to swap lane before the road forks. So here we can see some outcomes of the simulation. So the left-hand side, you can see predicted human responses in terms of longitudinal acceleration, longitudinal velocity for a given candidate a future robot trajectory. Now, the point here is that the interaction appears quite natural, and interesting behavior emerged. For example, in some cases, the robotic vehicle was nudging on the other lane to disambiguate human intent. But the point is this safe? And the unfortunate answer is that in general, this is not safe. In some rare cases, the forecasting model guesses wrong about what the other human is going to do. In this case, the human behaved in a way that defied the model predictions, and as a consequence, there was an accident. So probabilistic predictions are still guesses. And the point is that sometimes our CVAE-based model guesses it wrong. Rarely, but sometimes it happens that a human drives into us. More generally, probabilistic planning, even with fairly sophisticated models, can lead to unsafe behaviors, I would argue, for three main reasons. First of all, as I already mentioned, the probabilistic guesses may just be wrong. Second of all, collision avoidance at this level of the control hierarchy is typically incorporated as a penalty function within a much more complex aggregate cost function, thereby causing conflict of objectives. And finally, planning at 3-4 hertz is ultimately too slow to ensure safety. Now, this leads us to a key question, that is, how do we integrate safety assurance within a probabilistic performance-centric planning framework, such as the one that I just presented, but not necessarily the one based on our work. More explicitly, the big conundrum is how do we strike the right balance between safety and efficiency? High-level planners, such as the one that I just presented, typically leverage probabilistic reasoning to promote efficiency, that is, smooth interactions, at the cost of safety. While low-level planners typically leverage worst-case reasoning to promote safety at the cost of efficiency. Of course, ideally, you would like to be maximally safe and maximally efficient, as represented by the star here. But in reality, what we can hope for is just to strike a good balance between full safety and full efficiency. So basically, notionally, try to be in the green blob that I have in this notional plot. From a more technical standpoint, the key challenge is how do we glue a safety controller, which is typically based on optimal control methods, with a higher level probabilistic planner, which is typically based on machine learning techniques, such as the case for Trajectron++. And we want to do so in a way that does not unduly impact performance. And I would argue that, in fact, in the academic literature, such an interaction among different layers of the autonomy stack is often overlooked. Now, let's first discuss the design of the safety controller and then how the different layers of the decision-making stack can be glued together. Specifically, there have been several approaches in order to promote safety at the lower level of the autonomy stack. For example, potential fields, constraint optimization, pre-computed emergency maneuver libraries, and so on. These techniques, however, do not account for interactions with a sentient agent, basically decision-making agents, such as a human. Thus, they are difficult to glue with the decision-making stack that strives to enable smooth negotiations. In our work, to account for interactions also at the controller level, we harness the tools of Hamilton-Jacobi reachability. Now, reachability is often interpreted in a forward, open-loop sense, where human dynamics are propagated forward in time, and the resulting set is treated as a static obstacle. However, such an open-loop notion of safety can sometimes be too conservative for interactive driving. In our work, we instead focus on backward reachability, where joint dynamics are propagated backwards in time, accounting for the closed-loop interactions among the vehicles. This results in sets that basically encode the notion that you don't want to put yourself in a situation from which you cannot recover. And I would claim that this is somewhat similar to how I ride my motorbike, which is very different from how I ride my car, in the sense that I always try to put myself in situations that in case someone gets distracted, I still recover from. Basically, I can avoid a collision. Now, explicitly, a backward reachable set is defined as a set of avoid states for which there exist strategies for the human that for all inputs of the robot will lead to collisions. And of course, we want to stay outside of this avoid set, or if you are inside, we want to get outside the avoid set as soon as possible. These sets can be computed by solving the celebrated Hamilton-Jacobi-Isaacs partial differential equations, whose solution V, referred to as the value functions, gives the backward reachable set as its zero sublevel set. Now, this computation is very hard, but fortunately it can be done offline. Then the optimal avoidance control is the control U of R. Here, the subscript R stands for robots, and the subscript H stands for human. A U represents control. So the optimal robot avoidance control is the control U star R that offers the greatest increase in the value function V, assuming worst case actions by the human, denoted, as I said, with U of H. And this is something that has been investigated for the past couple of decades. However, previous application of a Hamilton-Jacobi-Isaacs solutions has switched to this control when near the boundary of the backward reachable set. Let's see what happens if we do so. So here is a case whereby we have two vehicles that are driving side by side. The red vehicle was the robotic one. The green vehicle was the human one. In this case, the human vehicle drives into the robotic vehicle, and the robotic vehicle switches its decision-making plans to the optimal avoidance control in an effort to avoid a collision. And then the result is that indeed the vehicle is safe. It basically exits the road and stops. So we achieve safety. But if every time that a vehicle that is next to us does something erratic, we were to stop, this will be safe, but from an efficiency standpoint, a mobility standpoint, will be disastrous. Nobody would use such an autonomous car for mobility services. So how do we basically decrease the conservatism of this approach while still retaining the strong notion of safety that stems from Hamilton-Jacobi reachability? Well, the key idea in our work is that rather than switching to the optimal avoidance controller whenever near the backward reachable set, what we do is to optimize in terms of safety-preserving controls. The set of safety-preserving controls, capital U of R, represent a set of robot controls that ensure the value function is not decreasing. This set, however, in general leads to complex, non-convex optimization problems. Thus, to enable computation at about 100 Hertz, which is typically what we need in autonomous driving applications at this level of the control hierarchy, we consider a linearized version of this set around the operating point. Then we set up a low-level controller that entails solving model predictive control problem, which is quite standard, in which we try to track the desired trajectory that stems from the higher level decision making, while accounting for linearized vehicle dynamics, stable handling envelope constraints, control constraints. So this is all very standard, but with a crucial addition of an instantaneous interaction safety constraint whenever near the backward reachable sets. That basically forces the MPC problem to reason about a safety preserving control. Now, we have also investigated formulations where the value function is added to the cost function to give to the controller an element of foresight. So the overall problem is a QP, and we solve it at 100 Hertz by using the operator splitting quadratic programming solver. So the idea is fairly simple. We have a reference trajectory that stems from the probabilistic decision-making plan, and then we build this kind of a shield whereby in the tracking process, we reason in terms of safety preserving controls whenever near the backward reachable set, the avoid set. Putting everything together, the overall decision-making module comprises a high-level machine learning-based interaction planner, producing nominal trajectories to a generative model of human intent, a reachability cache based on optimal control techniques that encodes the notion of relative states that are unsafe, that is, that might lead to collision despite our best effort, and a low-level safe tracking controller that executes controls that minimally deviates from the planner choice if the vehicles approach a set of unsafe relative states. Even though this framework is presented here in the setting of pairwise interactions, we have extended it to the case of interactions with multiple agents. Here I'm showing some experiments on the racetrack where we have an autonomous car, the one with the red roof, which is fully autonomous, so all the perception, intent prediction, and decision-making control is done on board. And the role of the human-operated vehicle is taken by an RC car. And basically in this test, we try to abuse of our algorithms. We ask the operator of the RC car, the small one with a mast. The mast is used in order to make sure that the small RC car is visible from the autonomous car. Well, we ask the person that controls the RC car to behave normally and then all of a sudden do something crazy. Here, the task is still to swap lane in a given amount of time. And you see that initially the RC car is driving normally, it's going straight, but all of a sudden it swerves into the autonomous car. And then the autonomous car smoothly gives control to the Hamilton-Jacobi controller and then switches it back. So the interaction is very uneventful, and that's really the point of this design. Going back to our notional plot, so we have actually the field tests represented on the right, and where we compare our method to a method where we only consider tracking without basically the Hamilton-Jacobi reachability constraint, which we refer to as optimistic, and a controller that switches to the AGI optimal models controller when near safety violation, pessimistic. And the results from our methods are presented in green. As you see, our method actually provides a sweet spot in terms of efficiency and safety with respect to the two baselines. Now, two additional points on the topic of safe control with learned human models in the loop. First, the framework I've just proposed makes a strong adversarial assumption about human behavior. And one would wonder whether this assumption could or should be revised, for example, to imbue a notion of a shared responsibility for avoiding an accident. In this context, at NVIDIA, we're working on developing a unifying mathematical framework still rooted in the Hamilton-Jacobi reachability that encompasses a spectrum of safety concepts from open loop, non-reactive control, all the way to closed loop reactive policies. And the hope is that by developing this unifying framework, we can better reason about the differences and commonalities among the many different safety concepts that have been proposed out there. And also, we can make some of the assumptions more data-driven. For example, what is the right level of shared responsibility we should assume from human agents on the road? This is, of course, a very hot topic in the self-driving car domain due to significant regulatory pressure. A second quick point I want to make here is that, of course, the decision-making control module does not operate in isolation. So, for example, in the standard See, Think, Act architecture for an autonomy stack, the uncertainty stemming from the perception module impacts the safe operation of the decision-making module, the think box here. One thus needs to capture the interactions across modules within an autonomy stack in order to build a strong assurance case for the overall system. More broadly, I would advocate that one needs to reason about upstream and downstream information flows through metrics that are cognizant of such interactions, and should also reason about appropriate representation of such information flows. Now, for example, in the context of trajectory forecasting, we're working on accounting for uncertainty sources that stem from upstream perception models and understand how that uncertainty affects the quality of downstream trajectory forecasting. For example, we're working on understanding how to propagate the perception uncertainty in terms of classification scores. That is, in the image on the left, each object, as it is typical, has an associated classification score. Currently, such information is not considered by most trajectory forecasting methods. So recently, we have devised a methodology that accounts for this uncertainty. It turns out to produce a much better condition forecasts for the humans. Complementarily to this, the outputs of perception systems are noisy, for example, with object classes frequently switching. And so some parallel work we're doing is how to build trajectory forecasting models that are robust with respect to this noise at the input. And here we're just scratching the surface in terms of the interactions that one would need to consider in order to really build a safety insurance case for an autonomous stack. Well, in the few minutes that remain, let me switch gear and talk a little bit about my work on safe control with learned dynamical models in the loop. That is, models of a system, not a human system, but a system that is very difficult to model by just using first principle. For example, the behavior of the gecko-inspired gripper that I presented at the beginning of the talk. Now, our take, the take of my lab, is in developing the theoretical foundations for learning models that are cognizant of the downstream application and thus are easier to equip with safety properties. To be more concrete, consider the task of motion planning and trajectory stabilization for a robot for which we assume we do not know the dynamics. Typical model-based reinforcement learning algorithms take the following approach. We observe trajectories, for example, in terms of state, control, next state, or state derivative. We run a regression algorithm to estimate the dynamics model, and then we use this model to generate new trajectories for the system to follow. But when we generate new trajectories for the system to follow, there is nothing in the algorithm that guarantees properties such as controllability or even stabilizability of the trajectories that are generated through this model. That is, this naive model-based reinforcement learning approach does not account for the downstream task of trajectory generation and control. So we have investigated algorithms to learn a model under a stabilizability constraints, which guarantees the existence of a robust tracking controller for arbitrary open-loop trajectories generated with a learned model. How do we algebraically represent such a stabilizability constraint? This is really the crux of the problem. Well, in our work, we leverage a contraction theory. And indeed, contraction theory can be used to derive a sufficient algebraic conditions for the existence of a stabilizing controller for any trajectory. This formulation basically prunes the hypothesis space by tailoring the learning problem to the downstream control task. We have demonstrated this approach on a quadrotor testbed, where the task was to learn the model of a quadrotor and then use it in order to plan an 8-figure trajectory. And we observed that this formulation resulted in significantly improved trajectory generation and tracking performance. In the right, in yellow, we show the actual trajectory that was generated. In blue is the reference. That's on the left. On the right, I show the case where we built a model just by using a regression system, a regression approach, without accounting for downstream performance. And actually, in this case, the quadrotor crashed. In particular, here, the computing models are not only dramatically better conditioned by adding these stabilizability constraints, but also much more data efficient. Now, of course, one could consider the mirror problem, whereby instead of learning a controller with stability guarantee, so instead of learning a model with a stability guarantee, one learns a controller with a stability guarantee. In this concept, in a recent paper that will be presented at RSS this year, we propose to exactly simultaneously learn a controller and its safety certificate in the form of a Lyapunov function. And I won't go too much into the details here, but basically the idea is to consider relative activation functions for the neural network that allows us to represent a neural network as a piecewise affine function. And then by leveraging this presentation and the fact that properties such as the fact that the function is a Lyapunov function can be checked by using a mixed integer linear programming formulation, we're able to jointly compute a learned controller and its stability certificate. Finally, the next step in complexity is to consider models that adapt online. And here we are pursuing two directions. In the first one, we merge and blend techniques from meta-learning and adaptive control, where the idea is to backpropagate through simulated adaptive control loops to train features that are better suited to the downstream task. So you see this recurring theme of adding more structure in the learning procedure so that the learning procedure is more attuned to the task of downstream decision making. So this is another paper that we will be presenting at RSS in a few weeks. And the other aspect is, okay, how do we actually gather the data in order to learn the model in a way that we still have safety guarantees? We have a recent paper that basically consider an iterative exploration scheme to, in turn, exploring and exploiting the environment to learn a model, execute a task, while under very mild assumption, retaining high probability guarantees for safety at all times. Again, fortunately, I don't have the time to go into the details here, but just wanted to provide a perspective on the different ways one can reason about model learning, offline versus online, and how in each one of these cases, one can infuse optimal control techniques to better structure the models and make them more attuned to the task of downstream decision making. Which leads us to the conclusion. So the overarching idea of the work presented here is to infuse learning-enabled components with particular structure for either making the machine learning model better behave or bound its runtime performance. In my mind, such a blending of machine learning and optimal control techniques is a very promising direction to enable safe learning-based control for robot autonomy. A few parting thoughts, as I already stressed quite a bit, is the need to learn models for the specific purposes of the control and decision-making tasks. So try to imbue these downstream decision-making usage in the learning process itself. Second, when is a model good enough? In general, one should strive for simplicity. A famous quote from George Box is that all models are wrong, but some models are useful, and everybody agree with this statement. But actually, people forget to cite the second part of that quote from George Box. This says, over-elaboration and over-parameterization is often the mark of mediocrity. So that's the second part of the quote from George Box. So accordingly, principal methods to assess when a model is good enough will be of critical importance for future robot research. Finally, no matter how good you are in designing your models, your control algorithms, during runtime operations, you might get some anomalies. So another aspect that actually our lab is getting increasingly, my lab is getting increasingly interested in, is how to devise runtime monitors that check the different data-driven learning-based components in the autonomy stack and make sure that they're operating nominally, or if they are operating in non-nominal conditions, we raise an anomaly signal that informs downstream decision-making, for example, in terms of enacting an emergency maneuver. And finally, of course, we talk a lot about safety certificate for a given control algorithm or decision-making algorithms, but in order to really have a robust systems, along with a safety assurance, strong safety assurance case, one, of course, really needs to reason about the robustness across the autonomy stack. And I can say, also given my dual role, both in academia and industry at NVIDIA, that this topic is still in, so understanding basically the interactions among the different components and building assurance cases that account for those interactions. It's a topic that is still in its infancy and really a pain point to deploy these systems. With that, I'll be happy to answer any questions you might have. And of course, I would also be happy to talk more about these topics offline.
Thank you, Marco. We are open to questions. You can write the questions in the chat or raise hand and I'll unmute you.
I can ask a question while people are thinking. Hi, Marco, thank you very much for a really amazing talk. I really enjoyed it. I have a question about the Hamilton, Jacobi, Isaacs PDE.
Yeah.
So you mentioned that as one promising approach for going forward. I was curious about, is it necessary to know the system model fairly well here? And how would this approach handle like unmodeled aspects and disturbances? So, for example, in the experiments you showed, what would happen if the road was icy or there was some other disturbance that wasn't considered?
Yeah, I mean, that's a great question. So there is an additional aspect of robustness for to model uncertainties that this does not account for. It really depends a little bit on your application. Right now, devising safety monitors, even for the simple case of driving on a highway in normal conditions, is already very hard. Taking into account robustness, super important problems. There are, of course, techniques one could leverage. For example, one could consider a robustified version of this AGI computation, or even bring in some of the techniques that I explained toward the end of the talk in terms of model adaptation. But I think this is a research topic very much in its infancy. And from an industry standpoint, we are very far from using those techniques in actual field deployments. So I think great question. There are some ways to infuse an element of robustness with respect to the dynamical uncertainties. As usual, you can take in a robust way, meaning you reason adversarially about some properties of the system, for example, coefficient of friction, or you can consider more a data-driven solution, possibly even with online adaptation. But then again, the complexity of building safety assurances in those cases, and actually a system that works, really compound.
Yeah, is there a way to, you mentioned model adaptation, which I think is really interesting, or I would agree that that's a very promising way. So I'm curious, do you think there's a way to adapt the value function online, or so you mentioned, or not even offline, but you mentioned some later in the talk, you mentioned methods that collect data and change the model. So do you think there's room to be changing the value function here? This maybe relates
in
to
my mind, it really
formulation.
Yeah, in my mind, it really depends on the application. So if we talk about ideally, that's what we want to do. If after 10, 20 years that we've done all this research, hopefully that becomes as mainstream as designing a PID controller. But right now, it really depends on the application. So if we talk about applications where humans are not involved, so basically if you fail, you do not lose a life, I think there is an opportunity out there to start fielding these technologies, and we're working with NASA in actually testing some of these technologies on a number of space robotics platforms. It's a need, and I think the theory now is relatively well developed to have strong guarantees that the model is not going to adapt to something that is not useful anymore or actually could jeopardize operation. From the point of view of, say, autonomous cars, we're far from it, both in terms of the extreme reliability that you need, and two, there is a whole other aspect that I haven't touched in this talk, which is the aspect of certifiability. So basically, certifying code that whose performance is highly dependent on the very specifics of the runtime operations is very hard, and right now I would say very difficult to accept in industry. So that doesn't mean that we shouldn't work on it. I'm just saying it might be much more complicated to infuse it in actual deployments.
Thank you so much. I really enjoyed the presentation and the discussion.
Thank you very much. And everyone online, if you have additional questions about this work, feel free to email me. I'd be happy to talk more about it offline.
Thank you so much. So we are